Hi. Hi everyone who's joining our webinar. It's a pleasure for me to be your host today. Another webinar of Principia. Today we've chosen a very basic topic. It's about how to use our app in general for simulation. So the last webinars covered more specialized topics and also some use cases with customers. Today I'd like to just show you what it is about, what is the topic itself, and also some live demos. So an agenda for today. Of course, I'd like to introduce myself and the company. Then I have a short view of the Principia app integrated in Onshape, just as an overview. Then some multi-body dynamics background. And then, of course, the most important part of today, the live demo, or also very important questions and answers. So I would be very happy to answer your questions regarding our product. All right, so who are we? So we are Principia MBS. We founded about a year ago, and we are a solution provider for design validation tools integrated into CAE platforms. So the term design validation is something we created to combine both, or to speak to both, to those who already know about digital or virtual validation, and to those who do some tests in real life. So to combine those two fields into design validation in general. We ourselves are experts in numerical solvers for modeling dynamical systems and algorithms. For dynamical analysis, we also are experts in UI UX design and web development in general. To me as a person, my name is Stefan Oberbeilsteiner. I've got a background coming from a technical college to the Upper Austria University of Applied Sciences, where I did my master's in mechanical engineering. And afterwards, I joined a research group for multi-body simulation and did my PhD at the Technical University in Vienna. My competences personally are in engineering and CAD design. So I've also some background in CAD design, where I did some jobs in this field, and also some private interests in CAD design. I have competences in the field of solid mechanics and simulation tools. And during the last time, I learned many things about method development and creating software using these methods. Now, let's come to the problem itself straight away. So directly to the problem. What is the problem? What we are talking about? So I've got a slide for you. It's something I did in my leisure activities. So I was into a racing team, and I was responsible for designing suspensions here. And if you see this picture, there obviously went something wrong. So it would have been a good idea to choose a simulation tool in this case. I tried to, but I was not happy with all the tools available for me at this time. So in this case, it was really the first test run where we invested more than 2 years in the construction and into building this racing car. And then in the first 3 rounds, this happened. And this was just due to some, say, not good chosen kinematics. It was not because of some material failure or something like that. It was just because of an insufficient planning of details. So what could be the solution for this? And that's why we are here today. It is all about doing this virtually, doing this testing virtually. So the video here shows our vehicle too. So it was just a few years after this. So after I've been all into the details of multi-body simulation, I was able to simulate suspensions. This is obviously the front axle suspension, what you see here, but with multi-body simulation, you are able to generate all the load cases acting on your product, and this all virtually. And there are many, many benefits of it. And one of them is you can create any measure you like, and you can cut into some details at any time. There is no limit in sensors. That means you can create any data you're interested in. And that's, say, the solution for all these problems where you have insufficient planning. Good. And now I'd directly ask you to answer a question. So I've got a poll, and I just started here. Let me see how we can manage this. So you should now see the poll in your chat. And it's all about, how does your product validation process currently look like in your company or where you're working in? So is it guess and hope, just like I did in this race car example? Or is it with real prototypes and a test rig? So prior to going directly to, in our case, to our first race, it would have been a great thing to have our car on the test rig. The third thing is simulation, or do you have any other idea? So of course I answer this with simulation, and I can see that there are several answers. So there is guess and hope. Yeah, I know that this is probably sometimes when simulation seems to be too complex, and it is the effort to do simulation seems to be too high, then guess and hope is for some the ideal solution. Real prototypes is of course not possible for everything and for every company and every project, because it really is, it is expensive. You have to provide a prototype that is acting on the test rig, and you also have to have all the equipment, so all the measuring devices, but also the actuators that are able or capable to provide sufficient loads onto your system. For automotive applications, this is quite expensive, of course. And I see that there are some of you answered with simulation, or most of you. This is, of course, the ideal case. And if it's something like our solution, when it's really integrated in the design work, in the design environment, like in Onshape, then of course this is also the cheapest and most efficient way of validating your product. All right. Thank you for your answers, and let's continue. So what is Principia? And currently our company is named Principia, but also our first product. And Principia now is also the app is named like that. So in Onshape, you can subscribe to our app in the App Store. And what you get is a side panel app that shows up in every assembly of a document. So you see it here with the green frame around it. This is a zoom in. So this is the modeling page of our app. This means we can collect all data from your Onshape assembly, and then we can add data that are necessary to perform simulations, and of course to get some, or to be able to analyze something in your system. It's all really integrated natively into Onshape, and we also reuse many things from the Onshape environment. And you will be able to see this in more detail, of course, afterwards in my live demo. So I talked about multibody dynamics, and I said this is the solution to many problems when it comes to creating loads or creating real-world scenarios with your product prior to going into prototyping. But of course, I guess that many of you know other simulation types, because multibody simulation is not doesn't have the highest popularity, so not everyone knows about it. So that's why I'd like to do another poll. It's always interesting for me to know which methods do you already know. So here I've got 4 for you: finite element analysis, computational fluid dynamics, multibody dynamics, and the discrete element method. So let's see if I'm able to add this again. Yes, so I launched it. Should be able to check some options here. Of course, as an alumni of a simulation master course, I should check all 4 of them. And I did. Yeah, so probably I should have asked if you knew them prior to this webinar, because now I see that 38% checked multibody dynamics as the method they knew, and this is has top ranking now. But I see that you also checked finite element analysis, or at least some of you, and computational fluid dynamics. None of you checked the discrete element method, because I think that's something very new. But let me just talk a few words about the method itself. So finite element analysis originally was designed to analyze only one solid body. So for those systems, we in multibody dynamics are on a system level. Nowadays, finite element analysis tools also allow to analyze interconnected bodies, but in the original version, this was not the case. So they were extended to do this. But in finite element analysis, everything is about stresses and strains. So how is does the deformation of a body look like, and how does this affect, on the one hand side, the strength of the part itself, but also not only the one-time strength, but also the fatigue details. In finite element analysis, there are different types: nonlinear and linear finite elements. And in linear finite element analysis, it is not possible to cover large deformations or large rigid body motions, which would mean if you model, for example, a pendulum that performs some angular motion, it is just not possible to cover that with finite element analysis. With applying nonlinear finite element analysis, this is possible, but it really needs a high amount of computational power. That's also why it is super slow in such cases. Computational fluid dynamics, here's all about the flow. So all about fluids, liquids, gases. It can be extended to combustion and all that stuff. So it's a complete separate discipline. It is not about solid bodies like in finite elements, but it's all about fluids. Multibody dynamics, as I gave the introduction, we do something with systems on a system level. There are several bodies, they are interconnected. Multibody dynamics itself originally had only rigid bodies, but many years ago already, there was an extension to it, or there are extensions to it, to also cover flexible structures within finite element, within multibody dynamics. In this case, there is kind of a pre-processing step of your bodies, and you have to create some flexible structures for them with the help of finite element analysis, but only for one time, and for all the other simulation results, this is not necessary. And the last topic here, discrete element method, it covers some rigid particles that can collide with each other. And with some special extensions, you can also do fluid dynamics with it, because you can create behavior for those particles that they behave like a fluid. And they can also behave like multibody or bigger multibodies. So it's something like a combination of methods, and it is very promising for the future, and it is also promising to couple it with solutions like ours. For example, to create environments for agricultural machines where you drive over fields, etc. Good. Now, let's come to more details about multibody dynamics. So what it is, basically, it is all about studying the motion and the behavior of those interconnected mechanical systems. So here I say the motion, it can be also used for analyzing static behavior. So the method itself is capable of computing static solutions. Although the name is multibody dynamics, in a subsection of the theory, you can also, of course, cover statics. Because when velocity is zero, this is also kind of a dynamical equation. But yeah, you can also cover this with MBD to compute the, for example, static equilibrium of a system. Analyze forces and interactions means that for solving these equations, it is necessary to also solve all the forces acting between these interconnected bodies. So as a byproduct of your, say, animation or motion analysis, you get all the ingredients that are necessary for analyzing things between those bodies. So you get all the forces, for example, if there are screws or rivets between bodies, you can directly observe if these parts that are interconnecting those bodies suffer from loads that are too high for this element. Of course, you can gain insights into system behavior. This is often the case when it comes to some vibration stuff. So when you have some effects in your system where some eigenfrequencies are excited, this is all about, you can gain insights. You then know why this is behaving like that. You can evaluate the performance, which means if you have some given constraints for some actuators, you can see what is the maximum performance of your system. Of course, you can identify issues like, is there any collision between parts, etc. And of course, the goal is to optimize the system as a whole, but also the components. So if you create some loads for special parts of your systems, you can then go into an optimization of the part itself. You redraw it, do some modifications, and check if this modification is better or not. What is MBD not? We are no finite element analysis tool, so you cannot do detailed analysis of structural deformations. We can serve as an input for finite element analysis, like I said, the loads, but you cannot do this detailed analysis of structures. And we cannot do any other multi-physics stuff like heat transfer, or thermoelastic behavior, or fatigue analysis on our end. So we can bring some inputs for it, for fatigue, but not the fatigue analysis itself. Then we are not computational fluid dynamics, so we cannot investigate any flow of fluids, gases or liquids, and we cannot deal with the interaction between the fluid and structure. So therefore, we would need a coupling to such a computational fluid dynamics tool. What can you do with multibody dynamics? Typical tasks are those three depicted here. And in more detail, we see first thing is functionality checking. So in my video, you see a subsystem of a 3D printer. And here we investigated a two-dimensional motion. So it's not the most complex motion, but you see there are two motors acting at the same time. And you can check. That's why it's here under the category of functional functionality checking. You can check if there are any collisions, if the motion really looks like you thought about. So in this case, there was also one output. It was the trajectory that is necessary for the PLC control. That was an output of this principia simulation. So with multi-body simulation, you can reduce the risk and costs associated with physical prototyping, because if you would have to produce the prototype and then find out that there is a collision, this is obviously kind of a problem and costly. Then the second task that can be done within multi-body dynamics tools is scaling parts and machine elements. So as you see on my pictures, there can be some joints like this ball joint, or some screws, some bearings, and all these parts have some certain limits, of course. And if you do not have any chance to create loads, or you only have guesses, this is very challenging to dimension those parts. If you have a tool like ours, you can compute loads or also load cycles. So that means how often this is loaded with this special amplitude. And then you can, of course, go into these tables or any other standard values for these parts and dimension those parts prior to going to prototyping, which of course is very beneficial. And when it comes to parts that are created or designed on your own, multi-body dynamics is the tool for creating loads or generating loads. Not the loads that are acting on the entire system. Of course, this could be something that is there, but more the loads that are acting between all these bodies. So most of the time, you only pick one part of your system because this is the critical one, or the one that had some failures in previous models or previous prototypes or products. And then you pick this part and you investigate the details. And if you only have some guesses for these loads, this is of course very challenging. And with multi-body dynamics as the tool, as the generator for loads, this is a quite easy thing. So those are the three typical tasks which are covered with multi-body dynamics tools. Now, this is the time for jumping into my demo. Good. In my demo, I'll show you a model you may have already seen. So this is the model we are distributing when you do your first subscription to our app. So it is just a very simple geometry, and I also have a video how to create this geometry for real beginners in both Principia and Onshape. So where do we start? Of course, in CAD, you always start with defining or creating geometry. In this case, I'd like to show you this chain model. And I've got only one of this linkage here in my part studio in Onshape. So I already did all the sketching, and I have an extrusion of my body. What I also did is I created some mate connectors in the part document, and it is always very beneficial, and it is something I'd really recommend for you to think about all the interfacing possibilities of your parts and create those mate connectors directly in the part studio. Because when you do some import or do the import into the assembly, and you have some more than one instances of the part, you already have all the interfacing points. And of course, it is also, in my opinion, it is much more easy to create those mate connectors in Part Studio without having all the other parts in the surrounding. Of course, you can hide all the parts in the assembly, but it is always beneficial to start with this in Part Studio. And we can also at this stage, we can already think about where could be some interfacing points. Then what's also very beneficial, if you do this, to give them a name directly here. So not leaving this with the default name, but I'd say we could say this is the chain link. This was the lower one, so this one, and I say this is chain link. Why this could be important, when you then go into the Principia app, you can of course pick all these made connectors in your Onshape assembly, but it can also be done by a drop-down menu, and if you give them a meaningful name, you are, at least in my opinion, faster. So provide some names for made connectors. That's the first thing, and provide made connectors itself, because you will need them to create a model. Then we have to think about the material as we try to do some simulation run. We of course need some material properties, at least the density, because Principia will directly pull out the inertia information from Onshape. So that's why at least the density has to be defined. In my case, my part is made of stainless steel, so I'm fine with this. There's also the definition for the Young's modulus and the Poisson ratio, which means for later contact model where we use this Young's modulus, we are already prepared. And then last but not least, it is always good to give the part a name, because part one probably is not satisfying, and we can also give them a name. More important, or it is more important when you have, of course, different parts. In my model, we only have this single linkage, but it is much more easy to work with Principia when you have some meaningful names, because they will also show up in other sections there. So not only in pre-processing, so during modeling, but also in post-processing when you show some results. Good, and when we are done on the part side, we can go to the assembly level. Therefore, I create an assembly. And I say this is my simulation model. And then we import bodies. So I'd say make a chain consisting out of 3 bodies. So I insert 3 instances of my link, and then I create a model out of it. So what I would like to do is I'd like to create one interface or one constraint, one made feature to the surrounding. So what I need here is, oops, sorry, I should have click OK. Sorry for this. So one made connector to the surrounding. That's the thing I need. So when I click origin, then this made connector is connected with my surrounding, and we always call it world. So whenever you see some statement in Principia that says world, this means this is something connected to your surrounding. It's not located on a body, but it's located on the inertial frame, and we call it world. So I created this this reference or this made connector on world, and I say this is chain link 1 to world. And what I also would like to do, as Revolut joints always use the Z axis as their rotation axis, I'd like to move it So in this case, I just rotate it 90 degrees about the X, and then I'm fine with having the correct rotation direction for my model. And then I can start to connect bodies. So with my Revolute joint, clicking on Revolute joint, I can hit both mate connectors, and then I do the same for all the others. In order to avoid the collision here, I just flip the orientation. And then in order to choose the right things, just use the kinematic solver of Onshape to create different configuration. And I add another Revolute joint here. So Revolute joint between the second and the third chain link. So I created a link consisting out of three, chain consisting out of the three links. They are not penetrating each other. If they would do, so if there would be some collision between parts, this is no problem as long as we do not use a contact or activate the contact between bodies. So this means we are fine with this. Good. And then something else. So an information for you. You may have observed that there are Revolute, there are redundant constraints. If you ever worked with Principia right now, you've seen that there is Revolute redundant constraints. It means if Onshape allows, or if Onshape finds that there is that your model is correct, that means you have some double fixed joints. That means you have connected your system to your surrounding 2 times, and it's something like over constraining. Onshape has an automatic detection of this. Later on in Principia, it can happen that we give you an error and say, hey, this is over constrained. So we do not automatically kick out all these constraints. This is because on our end, this has some physical meaning. So we only give hints what you could do in order to improve your model. Just as a hint, you may have seen this in Onshape that everything in the tree gets red, at least in the mate features. This is when you do some over constraining. Then Onshape covers this, but Onshape has also a feature to kick out these redundancies, and we do not do this automatically. All right, so many words for this. Let's jump into Principia. So when you click on the icon on the right, our side panel app shows up. And whilst the loading animation is there, Principia gets all the information via the Onshape API. That means all the body's geometry, the body's properties like inertia and material properties. So that's in the first section. So as we are in a multi-body system, this section is called bodies, as there are multiple bodies. What you can do here, you can also define some overrides. It means if you have some extra loads on a body, you can directly type them in here and change the actual mass of the body. So if you do not want to model a load like an extra payload, you can add it here. So nothing to be done for our chain, but this could be something in your model. Then the second thing, of course, you've seen that there is a fully defined kinematics here in Onshape. So in our app, we also import all the kinematics directly. So that's the thing here. We see we have 3 Revolute joints, and they are imported as constraints. So we call them constraints on our end. And we, of course, detect which type of constraint it is, and therefore, and due to this, we define the locked and unlocked degrees of freedom between those two bodies. So you see the involved bodies, and you see the degrees of freedom, which means here we have all displacement or translational degrees of freedom locked, and some rotational degrees of freedom are open, just according to the Onshape mate feature. If you want to, you can also override something. So if you want to create some special interfaces that are not available in CAD and probably also not important in CAD, you can do this here. So you can open individual degrees of freedom. This override also stays there if you update your CAD model. As long as there's this blue line, the override is active. If you hit the reset button, everything is just according to the Onshape model. Good. So bodies and constraints define the kinematic model. Now it comes to kinetics, which means we add the inertia and we add forces and we do some dynamical computations. So in kinetics, we want to solve the equations of motions just to natural things like forces, gravity, etc. In my case, I'd like to directly start without any additional force, only with gravity. So when you open the settings tab, you see that there is the gravity settings. So here, the vector of the gravity is defined. In this case, it's the default gravity on Earth acting in the negative z direction. So everything's fine here without any force. We can try to start this chain like a pendulum. What you see down there is that this button changed its color. That's just because I did some movement here with the kinematic solver, and we got this notification in our app. So you are required to hit this button if you want to have this new initial condition in your dynamics model. So this means we do not automatically update. That's just because of issues like when there are two people collaborating in one document. It of course would be a bit messy when there is an update in your multi-body dynamics model every time there is a change in a body. If you change a fillet in one body, it is not, in our case, we do not automatically update. But we inform you that there was a change, and you can also always enforce updates by clicking on this button. So you can ensure that everything's up to date. One thing that I missed here is simulation settings, which means you just have to define how long do you want to simulate and how fine should the output be by means of a time step size. The solver itself does its own stuff, so he uses this step size or finer ones if it is necessary. This is just for you to define more or less the frame rate for your video animation. Good. And if we hit the start button, we trigger a simulation run on our cloud servers. So as you see, this was quite a fast one, so it is already finished. So I changed it to the history tab, where you see all the simulations concerning this document. You see the name of it. You can of course always change the name, like labeling it for being able to find it afterwards with our search or in the list. So, and you can also see for those who are versioning these models too, in which branch or where this model was created, in which version branch. Good. You can also delete simulation runs that are no longer of interest. So if you hit this delete button, there is a double check. So see this. So I have to confirm that I want to delete it. So now I want to see the result. So by clicking the View button, I can see the animation. So as we assumed, the gravity is acting into the negative direction. We have a motion like a pendulum. So on the one hand, on the left-hand side, we can see the animation just to check if everything works fine. And if there are any collisions on the right-hand side, you see the XY plot. And in the XY plot, we can really dive into the model in full depth. So that means we can plot all the positions, orientations of bodies. Then we can post-process the constraints. So that means where they are located over time, position, and what about the forces between bodies in those constraint positions. And what else is here in the Viewer tab? Of course, in simulation, it is always about documentation. So when you create many variants of your model, it is sometimes hard to remember which setting was used for this model. In our case, this is of course well documented. So we see all the, if there would be some overrides, you can see it in the body section, but you can also see, of course, the gravity definitions and all the definitions if there would be a force. Good. So this is very, very basic. I'd like to just extend this model a bit to also use other elements of our software. So first, I'd like to create a sensor because, as I said in my introduction, that one of the benefits of doing simulation, and especially multi-body simulation, you can put sensors everywhere in your model, and that's not only cheap, it's free of charge because there is no additional computational power needed for doing this. It is something like a post-processing feature. But as you know, every details of your bodies moving around, you can, of course, compute any sensor reading you like. So if you hit this Add Sensor button, we first should give them a name because new sensor is not the best name and we cannot navigate through the drop-down menu later if there are many of those new sensors. So that's why I'd like to say this is the angular velocity link 3. So I'd like to measure the angular velocity of this part here. How to do this? So I select the angular velocity sensor, and then Principia asks me to provide two inputs, the to made connector and the from made connector. So from is the origin of my measurement, and to is the point where which I'd like to measure. As I said, we use made connectors everywhere. That's why we also use it here. So the to made connector is the position, the coordinate frame where we would like to do the measurement. And we can use it or pick it via the drop-down menu. So if we have a clever name like the chain link 3 lower, as I said, we gave it a name, then we can choose it here, or we can pick it with the pick in Onshape feature. So if we hit this button and then go into the Onshape assembly view, we can click this one. Good, and it is selected, stayed the same as it was the right one. If we want to measure this relative to world, so to our surroundings, so the absolute velocity, we could leave world center here, or probably we are interested in measuring the relative angular velocity between chain link 2 and chain link 3. So like if there would be a sensor located between those two bodies. Because obviously, or probably it is a bit hard to measure the absolute velocity of chain link 3 in this case with a sensor, with a real sensor. So that's why let's measure chain link 2 and chain link. So chain link 2 and use the mate connector chain link lower. So everything's set. We can hit the start button, monitor the simulation run. As I said, no additional computation power needed for sensors. And then we can find this sensor here in the dropdown. So, and you have three components, X, Y, Z. So angular velocity is always measured for all the components. You see some numeric noise here for X and Y. But you see the value, the absolute value is 0, at least for this floating number here. But for the Z direction, which is the one we have the revolute joint defined, we see this oscillation. So we see all the values in degree per second. So we use the units defined in Onshape for the output. So if you would change the degree unit, this would be, of course, updated. So this is basically everything I'd like to say about sensors. So as I said, put them everywhere on your system. It's free. And then forces, they are most important, I'd say. So if you hit this button here, add new force, you can again give it a name. Let's say use a constant torque, and we'd like to apply a torque acting on the first chain link. So that means it should accelerate and start to rotate around this axis. So we have several types of forces. Here we choose constant torque, and then we again have to define some mate connectors. In forces, it's not to and from, but it's action and reaction. So here I'd like to pick the chain link 1 upper, and I'm fine with having the reaction on the world coordinate frame. So it's between first chain link and the world. And then I have to choose where I'd like to define, or with which of these mate connectors or coordinate frames I'd like to define the axis the torque is acting. So in this case, I choose bound to world. That means I have to consider this coordinate frame on top. This is the world coordinate frame, and here I see the green one is the y-axis, and it should be the one I'd like to put the torque into action. So select Y, which is the green one here. And then I have to define the amplitude of my torque. Let's try with 10 Newton millimeters and hit the start button again. Good, so it does not start to rotate. I think this was a bit too low. So let's just directly try to increase the torque. That's benefit of having an integrated solution. We can directly iterate with having many different variations of our model. We can also, of course, change some details of our CAD model and hit the update button, and everything is already set for the simulation. So yeah, we accelerate. Probably 1 Newton meter is a bit too much for it. So we really start to rotate the thing like a propeller. Good. So this is it. This was the first model in Principia. We added some force, in this case, a constant one. We added a sensor. We've seen that there is a documentation of all our simulation runs with the time step included and everything else. And then we can jump into the viewer and see what is the outcome of our simulation. And of course, the documentation of the simulation run with having all forces and sensor settings defined here. All right. So let me just jump back. To my presentation. Good. So what's next for you if you not already have done it? If you want to try out Principia, we have a 30-day trial. Go to the Onshape App Store, search for Principia. We are in the category simulation, of course, and then subscribe to our app. We are very happy to have you on board. And if there are any questions, I think there are many channels how to reach out to us later on. But if they are, of course, now, you can directly ask them in our chat. Probably one question that was asked, already asked prior to this webinar, as we asked for it to post some questions. One of the questions was if it is possible to consider configurations in Onshape or of an Onshape model. Yes, it is. As we directly take over all the information from the assembly view, if you change something in your configuration or you change the configuration of your model, this is of course updated when you hit the update button. So this would be a good idea to show you this again in my model. So I've got a file here. So I have a configuration. So I defined the rotation angle of this first chain link. And I have two configurations. And you see it here is the default configuration and the config 2. I can also, of course, add another configuration. Let's say this is 11 degrees. And my assembly model just behaves like that. If I go into the Principia model, as I said, we take over all the information from the Onshape assembly view. And in this case, the same applies for changing the configuration. So you have to change it in Onshape and then everything's there in Principia. So let's jump to default. You see Principia is updating. That's just because Onshape also triggers the update in the application. And we can simulate with this config. So let's say this is the default one. And then for config 2, hit the start button, then config 2. And what we should observe, let's see. We should observe that the default or the default configuration is a fixing of the link 90 degrees, like that. And for this is the 45-degree initial position, like that. So yes, configurations are considered. Good. So if there are any further questions, I'm happy to answer them right now. If not, you can always reach out to us via different channels. And yes, as I said, start your free trial today, if not already done, and you're more than happy to have you on board. So I don't see any question. Sinan in the background, have you seen any question?
No, not any.
All right. And let's do this. Let's finish this. Thank you very much for your attention and get in contact with us. Good. Bye-bye. Have a nice evening.